Humanity has connected islands, crossed oceans, tunneled beneath mountains, and built vertical cities in the desert.
Yet there is one connection we still haven't achieved.
Europe and Africa, only 14 kilometers apart. After more than a century of proposals, billions of dollars, and some of the world's most ambitious engineering studies, we still cannot build it. Why? Because the Strait of Gibraltar may be one of the most hostile, volatile, and complex construction environments on Earth. To look across the Strait of Gibraltar from the shores of Tarifa in Spain is to witness an optical illusion. On a clear day, the white houses of Tangier in Morocco look close enough to touch. This narrow bottleneck represents one of the most glaring missing links in global transportation infrastructure. To the north lies Europe, a continent of 447 million people driving a highly industrialized economic engine.
To the south sits Africa, a rapidly growing powerhouse of 1.4 billion people with expanding trade ambitions.
Currently, global trade routes must rely on a continuous, sluggish conveyor belt of maritime ferries. Millions of tons of cargo, agricultural fresh goods, and electronics wait for hours, sometimes days in bottlenecked ports. A fixed connection between Spain and Morocco would instantly revolutionize international logistics, turning a fractured maritime corridor into a high-speed 120 km/h logistical conveyor belt. It seems so logical, so necessary, and at only 14 kilometers, deceptively simple. But when engineers first lowered heavy sonar equipment and deep-sea drills into the strait, the numbers coming back did not fit into any known textbook. The first shocking revelation was the sheer terrifying depth of the chasm. In engineering, the shortest path is almost always the chosen route. However, in the Strait of Gibraltar, the shortest 14-kilometer line happens to be the absolute worst path. Here, the ocean floor plunges down into a jagged, pitch-black abyss reaching a staggering depth of 900 meters. To visualize this, consider that if you place the Burj Khalifa, the tallest building on Earth, into this underwater canyon, its spire would still be completely submerged beneath the waves. Building traditional bridge towers in this environment becomes mathematically absurd. A suspension bridge would require support pillars nearly a kilometer tall just to reach the seabed, a feat that completely shatters our current limits of structural engineering and material science. Even if humanity could somehow manufacture steel columns of that scale, the ocean itself stands ready to tear them apart. The Strait of Gibraltar is not a peaceful body of water. It is a violent hydraulic battleground where two massive aquatic systems collide. The cold, less dense waters of the Atlantic Ocean flow eastward into the Mediterranean as a rapid upper current. Simultaneously, the highly saline, incredibly dense, and heavy waters of the Mediterranean sink to the bottom,
rushing westward into the Atlantic. This creates a permanent, dual-current system.
If you drop a vertical support beam into these waters, the top few hundred meters are violently pulled east, while the bottom section is dragged west with equal ferocity. This continuous, multi-directional force creates a massive twisting torque that would tear standard marine concrete and steel apart in a matter of months. Worse still, this boundary layer acts as a breeding ground for internal underwater waves. These invisible, deep-sea monsters reach up to 100 meters in height. While the surface of the strait might look like glass, these massive internal waves travel through the depths with the force of a runaway freight train, hammering anything in their path with unpredictable, catastrophic hydraulic shocks. Furthermore, the very ground beneath the strait is actively moving. The Strait of Gibraltar sits directly on the volatile tectonic boundary where the African plate and the Eurasian plate collide. Africa is migrating north, physically pushing against Europe at a rate of a few millimeters per year. For a massive, rigid infrastructure project, this slow-motion collision is a ticking time bomb. The immense tectonic pressure constantly builds up strain along local fault lines, triggering frequent severe earthquakes. Any fixed bridge or rigid structure built across this zone would have to withstand two continents, literally trying to crush it, making seismic design an almost impossible hurdle. Faced with these extreme barriers, history is filled with wild, visionary, and downright crazy proposals to bridge the gap. In the 1920s, German architect Hermann Zergel proposed Atlantropa, a mind-boggling megaproject that involved building a gargantuan hydroelectric dam across the entire Strait of Gibraltar. The goal was to deliberately lower the water level of the Mediterranean Sea, reclaiming vast tracts of land and generating limitless electricity for a unified Euro-African continent. Later, Legendary structural engineer T.Y. Lin designed a record-breaking suspension bridge featuring massive 5-kilometer spans. Other concepts explored floating bridges held in place by massive pontoons, the size of skyscrapers, anchored to the seabed by steel cables as thick as a human torso. But every single one of these concepts inevitably crashed into reality. Floating bridges would block one of the busiest shipping lanes on the planet, turning the strait into a demolition derby for 300,000-ton supertankers, while the extreme winds and waves made suspension concepts completely unrealistic. Then came the definitive engineering breakthrough. Recognizing that going over the water was a dead end, engineers turned their eyes downward and proposed a modern subsea railway tunnel. To make it work, they had to abandon the tempting, short 14-kilometer route entirely. Instead, they mapped out the threshold route, located further west. Although this path stretches the total length of the project to nearly 40 kilometers, it avoids the 900-meter abyss, maintaining a maximum depth of around 300 meters. The geology along this longer route is also far more stable, providing a glimmer of hope that humanity could actually pull this off. Building the Gibraltar Strait Tunnel would require pushing our most advanced construction technologies to their absolute limits. The project would consist of 2 main directional tubes for high-speed passenger trains and heavy freight rail, separated by a central emergency and ventilation tunnel. To dig through the variable rock, engineers would deploy specialized, pressurized tunnel boring machines. These mechanical titans, stretching the length of football fields, must carefully grind through the earth while counteracting the immense hydrostatic pressure from the ocean above. Because the tunnel would sit deep within a seismic zone, the concrete lining cannot be rigid. Instead, engineers must design an innovative, flexible interlocking segment system, allowing the tunnel to bend, shift, and absorb earthquake shocks without cracking or flooding. Additionally, a massive, highly advanced ventilation and drainage system would need to constantly pump fresh air into the depths and quickly remove any seeping water, ensuring the safety of high-speed trains hurtling between 2 continents. Yet even if the technical plans are perfected, the final barrier is not geological, it is human. A mega project of this scale carries a price tag that could easily exceed tens of billions of dollars, requiring unprecedented economic and political cooperation between Spain, Morocco, and the wider European Union and African Union. Coordinating financing, managing complex cross-border regulations, and addressing sensitive geopolitical issues like migration and security have slowed progress to a crawl. If completed, the impacts would be staggering. The tunnel would completely rewrite the rules of global logistics, creating an uninterrupted rail network stretching from the tip of South Africa all the way to northern Europe. It would slash shipping times, slash carbon emissions from freight transport, supercharge intercontinental tourism, and forge an unbreakable economic bond between Europe and Africa. The real challenge of the Gibraltar Strait Tunnel is not crossing 14 kilometers of water. It is overcoming everything hidden beneath it: the currents, the earthquakes, the shifting geology, the politics, and the astronomical cost. Yet history shows that whenever humanity encounters an impossible barrier, engineers eventually ask a different question. Not can it be built, but how? Whether this historic link is finally forged by 2040 or decades later.
One thing remains certain: the Strait of Gibraltar is one of the last great engineering frontiers on Earth.